Everyone, please welcome Parthe Pandit. Parthe is a core faculty member at C Minds IIT Bombay. Prior to joining IIT Bombay, he was a postdoc at HDSI UCSD. He obtained a PhD in ECE and MS in statistics, both from UCLA, and a BTech plus MTech dual degree in EE from IIT Bombay. His current research focuses on understanding the generalization behavior of interpolating machine learning models, such as neural networks. He also develops fast and scalable algorithms for training kernel machines. Over to you,
Thanks, Jatin. Thanks very much for inviting me, and thanks everyone for being here. So the title for today's presentation is hopefully not the best thing about the talk. Yeah, so old dog, old tricks, but there's some interesting stuff happening, I think. Before I delve into the technical stuff, I just want to announce a workshop that we are having next month.
Oh, that's why you said yes.
Yes. No, but yeah, you should register. Jatin has the link for how to register for this workshop. Hopefully, should be some fun deep dives into interesting topics. Okay, so let's jump right into it. Today we are focusing on supervised machine learning. I'm going to use this slide to set up some of the notation. Stuff is going to keep building up. So if you have questions, just stop me there and we'll have them clarified then and there. So what you're given in supervised machine learning is n pairs of inputs and outputs. Xi's are my inputs, yi's are my outputs. Inputs belong to some domain omega. I'm going to assume that omega is some compact subset of RD. And the goal is to find a map from this domain omega to R. So F is sort of the first class citizen of machine learning. And we want to do it so that it fits your data well. There are many different goals in machine learning like generalization, robustness, and whatnot. So yeah, I'm just going to leave things a little vague here. The standard way in which we typically choose a particular F here is by solving an optimization problem. The optimization problem consists of, the objective function consists of two terms. The first one is some kind of a data fitting term. So this is going to look at how good the evaluations of the functions are on your training inputs. Right? So fxi to fx1 to fxn and y1 to yn. So this is what is called the loss function. And the second term is some kind of penalty on how rough the function is that you choose. You don't want functions that are too rough because nature is not as cruel in some sense. And so this is your regularization or structure enforcing term of sorts. And one class of methods. So here the optimization was on some search space H, right? This is a space of functions. One class of methods that people have studied in machine learning and statistics is what are called non-parametric regression methods. And the idea here essentially is that the space of functions H is mathematically very precisely described to you, but it may not be operationally very precise for you to use in order to come up with an algorithm to do this search or optimization. Right? So one such example is written here. This is a Sobolev space of order 2, which consists of twice differentiable functions, which are 0 at 0. Their first derivative is 0 at 0. And the second derivative is twice integrable or square integrable on the domain, which is 0, 1. Right? This is mathematically very precise, but how am I going to actually do a search in this space of functions? It's not very clear. So the old dog in our story is what are called kernel machines. And essentially, they're solutions to non-parametric regression problems when the search space H has some nice structure. So H, whenever it is what is called a reproducing kernel Hilbert space, this sort of an infinite dimensional optimization problem has a nice solution. And that is what is called, there is this theorem The earliest version of this theorem I know is from Baba and Kemmelsdorf in 1970. It says that even though your search space is over this infinite dimensional space of functions, the optimal solution to any optimization problem of this type is always going to have a finite representation in terms of finitely many parameters. Right. So this essentially reduces the search from an infinite dimensional space to Rn, where you have to search over the coefficients of these this linear combination of basis functions.
So you're not told us what is a kernel machine.
So this kind of a function is what is called a kernel machine.
But what is it? Is it linear or diagonal?
So the function is not linear in the input. So this can be very non-linear in the input. It is linear in the parameters. So that's the nice flavor of this class of functions. Okay. It essentially allows us to extend everything we know about linear models to non-linear functions that are linear in the parameter but non-linear in the input. Right?
No, but my question was, are these functions given to you? Are they a standard form? Like what?
K is given to you. Yeah. So I'll describe how K relates to what H is. There's a one-to-one correspondence between every K and every H.
Okay.
Okay.
But given an H, you may have many Ks.
Yeah, given an H, you may have many Ks, unless you enforce some maybe extra conditions and then kind of get around that. Yeah, the kernel machines used to be sort of the state-of-the-art models until 2012, and then deep neural networks kind of took over the entire landscape of what happens in machine learning. But recently there has been some resurgence in studying these kernel machines again. Yeah.
So is n small n known to you?
Yeah, small n is the number of samples in your training data.
Oh, okay, okay.
Right. And whatever we understand today about deep neural networks, much of it comes from our understanding of kernel machines. Which
I have the n upstairs, the number of samples of the n
yes.
in the linear combination.
Yes.
They are the same.
They are the same. Yes, they are the same. Yeah. Yeah. Okay. Yeah, so that's how I kind of got interested into studying this class of functions because I wanted to understand what was happening inside deep learning. Turns out that kernel machines are more interesting than deep networks are. So I kind of got sidetracked a little. Okay. How to choose a kernel function is a separate topic of its own. I've written some papers on what is the effect of the choice of the kernel function on the quality of the function that you end up learning in the end. Yes.
So suppose I could show that there is no way to approximate it using a standard set of kernel functions until n is unless n is very large. This would therefore give me a lower bound on the number of training samples. Is that right?
Sorry, can you?
So I'm just trying to relate to something that I know.
Yeah.
Maybe I'm making.
No, that's fine.
Yeah. So suppose I have a way of proving, given a hypothesis class H,
Right.
from which you will choose your kernels. Suppose I could write that you need a large number of such functions so that the linear combination can approximate well with respect to your loss function. Let's say.
Yeah.
My target function F.
Yeah.
This would basically therefore amount to proving a lower one on the number of training samples.
Yeah, effectively.
Like
yeah.
Sampling, or like in the back model, we have some kind of like the sampling complexity and so on. So the same.
No, but this
I'm not sure.
This here essentially proves that you will have the.
Yeah, this is just a statement about what the optimization solution is going to look like.
Like this for every.
More generally, what the behavior of this function is a separate matter, statistical matter that.
Loss function here.
Yeah, this is true for any loss function. This does not have to be a convex function or anything. This is the best f in a particular h here, and that h is what determines what this k is.
And number of samples can be anything.
Yeah, number of samples can be anything. As the number of samples there changes, the number of linear combinations you have to take also changes.
I see. So here you're fixed here, n. So.
Yeah.
Okay.
Yeah.
broadly, Parthe is right in the following sense that when K is fixed and the problem in nature that you're trying to solve is also fixed, then if the function that appears in nature requires, let's say, lots of these K functions to be added together to approximate it,
Okay.
then that implies that the N you need here is also very large.
Yeah, right.
So that is indeed a low bound sum of complexity.
Correct.
And
Yes.
in fact, real sum of complexity could be even higher because the other errors also happen.
Right. Yeah. You're kind of exposing yourself to too many problem dimensions here in some sense. But yes, this is all you can pose all these questions very nicely in the framework of reproducing kernel Hilbert spaces. Yes.
Yeah, for example, I mean, like there's this VC dimension, right? So if I prove a VC dimension lower bound, then that in the
Would-
back model gives
Correct.
the
You
lower
would
bound,
give you yeah.
So it's the same thing.
Correct. Yeah. Okay.
One more.
Yeah.
This combination, is it guaranteed to gain edge?
Yes. Yeah. So this is kind of I'll get to that in just a second. Yeah. Okay. So the choice of how good this actually is depends very seriously on what the choice of the kernel function K is. We have a very nice paper on how to choose a kernel function that can actually beat neural networks in terms of their performance. For today's talk, I'm just going to assume that the kernel function is fixed for you, and I'm just interested in solving this kind of an optimization problem. So today's talk is not really statistical as such; it's an algorithmic talk. It's about coming up with an optimization algorithm for solving this, given the constraints of the problem and the structure that exists in this problem. Yeah. Okay, so here are some sort of desirable properties I'd like an optimization algorithm to have. One of them is that I'd like this to be a matrix-free algorithm. I never want to store what are called kernel matrices. I'll define what kernel matrices are, but I can only assume that I have the ability to take these products. Given a vector alpha, I should be able to take a matrix vector product of this type, where kxz is the pairwise evaluation of the kernel function of elements from the set X and elements from the set Z. Right, this is a matrix times this vector. Right? I should be able to do these matrix vector evaluations without storing the entire kernel matrix. Right. So one row at a time, you evaluate the kernel functions and you delete them immediately. I like the algorithm to be batch friendly. In the sense I should be able to process one bunch of samples and make an update immediately. I don't want to wait for the entire passing over the entire data to just make one update. I like stability. So in the previous slide, there was a regularization parameter lambda. I like the ability for the algorithm to be stable when lambda is actually 0. Because in practice, it turns out that lambda equal to 0 gives you the best performance empirically. So we like algorithms that are stable at lambda equal to 0 plus, and also at low precision. We don't want something that only works in double precision but breaks down when you work in single. Yeah, we also want some kind of memory efficiency and good GPU utilization. We want to make maximal utilization of all the resources that we have access to. And we want an algorithm that is general purpose. We don't want something that is tailor-made only for the Gaussian kernel or something like that. We want to just write one suite of algorithms that you can plug and play with any kernel. Okay. Seems like a lot, but again, I didn't make this slide first and then discover the algorithm. It kind of went other. Okay, so there are some existing options which I have some issues with them. The first one is this conjugate gradient kind of methods. This set of methods is nice. Unfortunately, it's not batch friendly. It actually requires me to take a pass on the entire data just to make one update. And it's also not numerically very stable for single precision arithmetic. So another set of methods are based on coordinate descent. And the nature of the problems here is that these kernel matrices are very poorly conditioned. Their condition numbers are really large. And injecting this preconditioning in those coordinate descent algorithms seems to be quite non-trivial. So That's one of the challenges that prevents using just coordinate descent methods. Okay, so what is the old way of training kernel methods? Maybe 10 years ago, 12 years ago. So here's the general framework. You have this sort of a minimization problem in the RKHS. You first use the representative theorem, which tells you that any function that you're going to have, the optimal solution is going to be of this form, k dot x alpha. So this k dot x alpha is nothing but the summation that I wrote in terms of the linear combination of the bases, right? And then you solve this sort of a finite dimensional optimization problem over f alpha, right? So you search only over functions f alpha that are parameterized in this manner, right? Now, once you've done this, this is just an n-dimensional optimization problem. You can use your favorite first order method to solve this, something like gradient descent, for example. Right? So this would be how you would write gradient descent. At the end of your gradient descent, you'll get an alpha. You'll use that alpha to get your estimate f alpha. Right? So here is what it looks like for the square loss. You first write it down in this manner. So fxi minus yi whole square. You now parameterize f as something like this, k dot x alpha. When you write it out, it becomes exactly this. So kxx is your square matrix, the kernel matrix, kxx alpha minus y whole square. Right? Nothing complicated here. You can do this with gradient descent. This is what your gradient descent update looks like. This is what your stochastic gradient descent update looks like when you're processing only one batch at a time. So one thing to notice here is that SGD requires you to update all the coefficients at every step. Right? This is how SGD looks like in this particular framework.
Here the input is only fxi and yi, but in the general figure the input was xi, fxi and yi. So are those loss functions also?
They also give you kernel methods. People don't typically come up with loss functions that use xi differently, but the framework allows you to use xi. Maybe we haven't reached problems that require you to choose loss functions in that manner. Okay, so what is the new show? We're just going to reorder the devices, and seems like something interesting is happening when you do this. Yeah.
Someone frozen some choice of k.
Yeah, I've frozen the choice of k. Yeah, throughout this, k is fixed.
I just like to hint that there is some optimal way of computing. Could you also optimize over k here? So that is not correctly defines k.
That's not this talk.
That's not this talk. Yeah, that's a separate talk entirely. But yeah, you're absolutely right. The choice of k is very important. So in just to make a comparison with neural networks, every neural network architecture has an equivalent kernel function that sort of pops out of it to describe the behavior of gradient descent kind of algorithms on the neural net. So this is what is called the neural tangent kernel.
Why are we trying to improve? What is wrong with this?
What is wrong? We would like algorithms which satisfy all of these properties, and this is problematic because this has dependence on the condition number square. We would like something that depends a little better on the condition number of the kernel matrix. That's basically it. Yeah.
So could you repeat what the representative theorem part does?
The representative theorem tells you that when you solve this infinite dimensional optimization problem, any optimal solution to this infinite dimensional optimization is going to have a finite representation in terms of n coefficients. So the solution is going to have a representation with n coefficients only.
And that part gives you the representation.
Yeah, that is the representative theorem.
So in order to write this triple equality, that line is
Yeah, this basically says that you, instead of solving this infinite dimensional optimization, you solve this finite dimensional optimization on Rn, and that gives you the same solution.
Okay.
That is what the representative theorem enables you to do.
Okay.
Yeah.
So given let's say you have found out your linear combination, then why are you using the first order method after that? Like, what is the system? What is representation is?
Yeah, but I still need to find the alpha, right? Like which alpha is that is important. Yeah, alpha is a free parameter in some, or n free parameters. Yeah. Okay, so the new show is I'm just going to swap the order in which these two things are applied in the previous show. Right, so we're going to do the following. The design philosophy here is that we're just going to work with first order methods directly in the infinite dimensional function space. Okay, and we know that the solution to this optimization problem has a finite representation. So we are going to hope that we'll be able to track all trajectories of first order optimization algorithms in the infinite dimensional space just using a finite representation. So I'm going to write down an algorithm on paper, right? This I can't actually represent in a computer in some sense. Without the representative theorem, I can't represent. But the representative theorem tells me that every solution is only of this form. So I can actually represent some trajectories in that infinite dimensional space. Okay, so that is going to give me an update equation on the coefficients. And what I get at the end is essentially a solution to the original optimization problem.
So how are you implementing this on computer?
So then I'll get an update equation that is still in alpha. It's going to look very different than the update equation which we had in the previous slide. But what it's doing is it's tracking the infinite dimensional first order algorithm.
But there's a big, like, so the reason this works in the finite dimension case is that dual space and the space are the same. But in the infinite case, that might not be the case. The gradient can be in a different space altogether. But that is where already the
right. So the nice thing is that the gradient also always lies in these spaces.
Because it's really a finite
right.
problem.
Yeah. It's really a finite dimensional problem in some sense. Yeah.
So this RKHS condition is baked into this. So essentially, like representer, first order, and then representer, right?
Not really. So this is truly a first order update equation in the function space. This what I'm using here is a functional derivative.
But that is in a different space, right?
That is in a different space entirely.
That these were the same is a very finite dimension.
Correct. Yeah.
But yeah, the reason that will work out is because of
Correct. Okay. So now we'll go through a laundry list of first order algorithms and keep making some minor improvements in every version of that. So let's start. Okay, before we go, what are the stakes through all of these contributions that we've made? So if we were to train a model that is of size 1 million centers, right? So 1 million linear combinations. The state-of-the-art algorithm, Falcon, this was a paper in NeurIPS 2020. This runs out of memory because it needs 4 terabytes of RAM just for the training procedure. Right? In the ICML 2023 paper, we proposed this EigenPro version 3 algorithm, which was able to solve this in 10 days. Okay, using very small amount of RAM. And then we realized that we're doing something very stupid. And so NeurIPS 2025, we had another paper which finds the same solution that EigenPro version 3 finds, but in 21 minutes. So this is like some sort of careful engineering work that we've done in going from here to here that allows us to cut costs quite drastically. Okay. This is a little, the 700x is a little unfair. What we actually now have is an algorithm which scales, whose runtime scales linearly in the in the size of the model than quadratic. So the EigenPro version 3 had a complexity which was quadratic in the size of the model, whereas now it's linear in the size of the model.
Engineering, where you go from quadratic?
Yeah, we could amortize some costs. So this order p square, order p is actually the amortized cost because of some trickery that we've done. You'll see what that exactly is.
So what is p? What is value of p?
P is sort of the number of linear combinations that you're taking in the model. So yeah, we actually, when you want to work with very large data, you only have a budget of p. So you have to throw away some objects in the linear combinations. Yeah. So when you want to work with infinitely large data, you can't actually store n, right? So this sort of compromise you make.
And p is sampled uniform.
We'll get to that. Yeah. Okay. Okay, so here is a quick introduction to RKHS and how to actually do first order descents in RKHS. This is my favorite book by Leuenberger, Optimization by Vector Space Methods. I highly recommend if you've not seen this before, just take a look. Okay, so what is a reproducing kernel Hilbert space? We've been talking about it at an abstract level. Let's get a little more concrete. So this is a Hilbert space of functions with what are called bounded evaluation functionals. So what is an evaluation functional? You take the map that takes you from f to f of x. So this is an element in the Hilbert space. This is an element in R, right? This linear functional has a finite norm. Whenever this happens, your Hilbert space is a reproducing kernel Hilbert space. It has this nice property that all these delta x's, the evaluation functionals, are generated using a single kernel function. Okay, that's why it's called a kernel function, which is unique to the RKHS. Sorry, you were saying that for every RKHS there could be multiple kernels that.
I thought you could do some transfer.
Yeah, there is some corner cases that you have to be a little careful about, but by and large they're unique from an operational point of view at least. Okay. So what does this reproducing property really mean? It means that when you take the dot product of f with k dot x, this function is also an element in the Hilbert space. You get exactly this f of x. Right? This is the inner product in the Hilbert space that you're acting. Okay. So let's go back to the Sobolev space that we defined earlier of order k equal to 2 in one dimension. The kernel function has a closed form expression. It's the integral from 0 to 1 of some complicated looking function. But something you can actually compute on a computer. This you can define for or for different orders. So this is for k equal to 2. You can define it for arbitrary k's. You will get more and more smooth functions as you keep changing the order. Right? So more operational definition for this Hilbert space is that you take the span of all the basis functions k dot x for all x in your domain, and then you take the closure of this span, and that is what is the RKHS. Yeah.
I have like a super general question. So, is there a way to tell whether a certain Hilbert space is an RKHS or not?
You look at all the evaluation functionals. Right. If you can certify that all evaluation functionals have a bounded norm, then it is an RKHS.
Oh, okay. So then always there will be
there exists a kernel that generates this.
And it's not simply saying, okay. So when is it supremum?
Yeah. Supremum of f of x. This is a scalar.
Right.
Over the ball, unit ball of functions in the RKHS, yeah. in the Hilbert space, which you are trying to test whether it is an RKHS. Yeah.
This would be clear.
This is the this is a very celebrated paper from 1950 by Aaron Sein on RKHS. That's I think on the RKHS, or that's the name.
Yeah.
Okay. So how do we actually operate in this RKHS? So it helps to define some more notation. So I'm going to use k dot capital X to denote the operator from Rn to the Hilbert space, and this is how it actually acts. K dot x alpha is this linear combination k dot xi alpha I. Okay, I'm going to use this subvector notation. So y sub b, where b is some subset of 1 through n with size small b. That's the subvector of y. And similarly, xb is the subset of x with indices with xi's that I from b. And similarly, f of xb is the vector of all the evaluations of f of xi, I and b. Right? Okay. Now in the RKHS, you can define the generalization of a directional derivative, what is called the Frechet derivative. Okay. So just like so let's say g is some functional that takes you from the RKHS to the real numbers. Then you perturb that at some point f by a delta h. H is an element in the RKHS. Delta is the size of the perturbation. You look at this difference and you take the limit of the perturbation to 0. What you get is an object of this type. So this here is a dot product of some function in the RKHS with the function h, the direction in which you're going to move. Right? This is the generalization of directional derivatives, where the direction in which you're comparing is h, and f is the point at which you're computing the directional derivative. Right? Okay, so the directional derivatives are the gradient is an element in your Hilbert space, and the Hessian is a map from the Hilbert space to itself. Yeah. So let's look at one example. So when you have just one term with square loss, half of f of xi minus yi, and you look at the gradient of this with respect to f, what do? You do chain rule. So you get 2 times f of xi minus yi times the gradient of f of xi, right? So this is the gradient or Frechet derivative of f of xi. F of xi is a scalar. Okay, now what do you know about f of xi? F of xi is nothing but the dot product of f with k dot xi, right? So this is like gradient of A transpose x is A, right? That you've seen. So this is exactly that, the generalization of that in the function space. Okay, so now if I have the square loss, I can write the gradient of the Frechet derivative of the square loss in exactly this manner, right? Aggregating all these terms, and in a clean way, I can write it this way: k dot x using the notation from the first line, and this is nothing but the residual on x and y. Right? I can do the same thing with a stochastic gradient, right? If B is some mini batch of indices, I get exactly this: k dot xb times the residual on xbyb. Okay, so we are now ready to actually track stochastic gradient descent in the RKHS. Okay, so this is what I want to do. This is the function that I started with. This is the function I'm going to. So this is alpha plus. Okay. And this is the update that I made, which is the stochastic gradient update. What is exactly happening here? This is a function with some weights alpha. This was the previous function with weights alpha, and this is another function whose weights are the residual on xbyb, and I'm only updating the coefficients corresponding to the batch, mini batch, right? So how do you track this in Rn on a computer? You do exactly this. You update only the b coordinates for the batch by exactly what is the residual on that batch. Right? So this update equation is going to track stochastic gradient descent in the RKHS. Is this clear? Okay, there is a nice theorem that tells us that stochastic gradient descent with a fixed step size converges at a linear rate to what is called the minimum norm interpolating solution if you start at 0. Okay. So what does, if I were to rewrite this statement, it tells me that I require kappa times some log 1 over epsilon steps. Kappa is the condition number of my Hessian, which happens to be some operator. We'll see what that is. And the condition number is nothing but the first to the nth eigenvalue of that Hessian. Yeah. Okay.
From the update, I can see the difference between switching the order. So if you are done with the first and then first up order, you only update alpha rather than updating this kxb. Is that the only difference, that the matrices itself are coming in, getting updated and not reviewed?
Yeah. Yeah.
Matrix is not really clear.
Yeah.
The case one. K is fixed. Yeah.
K is fixed.
Not K.
The coefficients alpha, I think that's what he was referring.
So I guess what's going on is that, by the way, in this way, you are only updating the b coordinates,
I am only updating the B coordinates.
Instead of all the coordinates, which would have happened if you had done the other way.
Correct. The other thing is that the condition number depends on this is the condition number of the matrix, not kappa square. If you had done SGD in the other way, you would have kappa square show up because the Hessian would be the kernel matrix square. Right? Here you only have one kappa. Yeah. Okay. So here is one issue that needs to be fixed immediately. Now, assuming a parallel computing model, if you were to plot the speed up of the stochastic gradient descent versus the batch size on the x-axis. So y-axis is the speed up, x-axis is the batch size. Right? There is a sort of linear scaling regime until when you can actually keep increasing the batch size, after which you start saturating. The time it takes to converge saturates because you need to take more steps of stochastic gradient.
Is it more steps or is it just that you cannot do them in parallel?
You can do them in parallel if you have a bigger GPU.
No, but then, so what's the parallel part here?
I'm assuming that you can process the entire batch in one time step, sort of.
Oh,
that is the parallel computing model, right? If you take me from
no, like it's not like restricted in how many, like what the batch size can. From where saturation coming? Saturation coming because
the saturation comes because of SGDs.
The limit short is just gradient descent, right? So
correct. So gradient descent.
Behavior is of gradient descent. That's what you.
Yeah, correct. Yeah. Okay, so the critical batch size is inversely proportional to the largest eigenvalue of the Hessian. Okay. Now, if I were to somehow do some preconditioning that reduces the effect of the largest eigenvalue, I would be able to increase my critical batch size, and I would also be able to increase how much speed up I am able to get, right? Because I can sort of essentially extend this linear scaling regime to some large number, right? So I can get significant speed ups in that manner.
So you take a batch and in that batch you look at the kernel matrix and then you compute sigma 1 for that.
No, the sigma 1 is the sorry, I didn't understand.
No, what is sigma 1?
Sigma 1 is the largest eigenvalue of the kernel matrix. I don't actually come.
You have a data set, no, for that data.
Yeah, for that data set.
Yeah. But it's not for the batches, for the entire data set.
Yeah, for the entire data set. Yeah. I don't ever have to compute sigma 1. This is kind of analysis that people have done for SGD that tells us the scaling behavior with batch size. Okay, so this is one peculiar property of kernel matrices that their eigenvalues decay very fast. Okay, so if I were to do preconditioning, that reduces my condition number from sigma 1 over sigma n to sigma q over sigma n. Sort of, I want to eliminate the effect of the top q eigenvectors of the Hessian in some sense, using my spectral preconditioner that I'm going to talk about next. And this speed up can, in practice, is very, very dramatic actually. It's like 2 orders of magnitude. It goes from taking days for convergence to minutes to convergence. Okay. And then it also helps me better utilize my GPU resources. Earlier, my critical batch size was much smaller. It was 1 over sigma 1. Now it has gone up to 1 over sigma q. So I can better utilize my GPU. I can actually tune Q so that my GPU is fully utilized in some sense. Okay, so what does preconditioning actually look like? So P here is some kind of a preconditioning operator that I'm now going to use. And how is this spectral preconditioner defined? So we do exactly the following. You look at the Hessian of this particular loss function. It is an operator that takes from the RKHS to RKHS. And suppose sigma I, psi I are the eigenpairs of this Hessian. So H psi I is equal to sigma I psi I. Right? These are my eigenfunctions. Then I'm going to define the spectral conditioner in exactly this manner. This is a standard object people define in numerical linear algebra. what it does is that the largest eigenvalue of the preconditioned Hessian is sigma q down from sigma 1. Okay, so this is now a much better conditioned matrix. And now SGD, this preconditioned SGD now converges in kappa q log 1 over epsilon steps. Yeah.
Like by preconditioning, you mean you're projecting onto smaller subspace, right?
Yeah, something like that. Yeah. Yes. Yeah.
Do you have the eigenpairs? Like the random-
That's a good question. I'll get to exactly what the eigenpairs look like and how to actually work with them. If you remember, we defined this operator k dot x, which was from Rn to H, right? The Hessian is this an transpose, and the kernel matrix is nothing but an transpose an, right? They're both gram matrices of the same object. And so if you do a singular value decomposition of A, that relates the eigenfunctions of the Hessian with the eigenvectors of the kernel matrix. Right? And now all we need to do is the eigenfunctions are exactly given by the eigenvectors of the kernel matrix. Yeah, this is some algebra that we're going to need in the next slide. So if suppose I were to do preconditioning by eliminating the effect of the first eigenvector, right? So this is what my preconditioner was. This is what my preconditioned gradient is. Okay, I do some algebra and I find out that the preconditioned gradient is just the stochastic gradient term that was there before, and there is some extra term. This is also a new function that I now need to subtract from the gradient. It's sort of a correction term that I get from the gradient.
It's a short question. So, I guess I don't know preconditioning. So, okay, so is it fair to say that if you were to do preconditionings perfectly, like if you could take like equal to n, then
it's exactly the Newton method. Yes, it's exactly.
So there's a sort of interpolation between for Newton and
yes,
product. Yeah.
Yes, exactly. Yes. Okay, and so here is what the preconditioned stochastic gradient update looks like. I do the stochastic gradient update and then I do a correction term. This E transpose is some kind of a low rank matrix multiplication.
I'm trying to make sense of, so this is like some kind of like generalized projective gradient descent kind of algorithm, right?
Yeah.
With the word generalization is to be taken very liberally.
Yeah, I mean, the thing is, yeah, you have this.
There's no projection of the project.
Yeah, it's not really a projection, it's a.
So the word generalization is doing all the heavy lift.
Yeah, okay. Okay, so one bad thing about this is that I need to calculate q eigenvectors of the entire kernel matrix, which is really expensive. This is the setup cost that I have to pay, which is expensive. I also need to store all the eigenvectors, which is also expensive in terms of memory. The number of flops that I spend per sample processed is something like n times q divided by b. Q is the number of eigenvectors I'm deciding to truncate. So here is we don't like this. We want to get rid of these costs. By the way, the name EigenPro is actually eigenspace projections. So yeah, there is some projection kind of thing happening at the back. Okay. Yeah, maybe very quickly, I'll skip this one slide. Okay, so we want to approximate the eigenfunctions without actually calculating eigenvectors of the entire kernel matrix. We want to do this somewhat faster. And there is this very neat way of doing that using what are called Nystrom approximations. So what you do is you calculate some submatrix of the entire kernel matrix. You calculate the eigenvectors of that submatrix of the kernel matrix. And you do an extension operation or the Nystrom extension that allows you to approximate the eigenfunctions of the Hessian with something which is much simpler. So these are eigenvectors of this KSS, and I just multiplied by this K dot XS to get the eigenfunctions. So this is a cheap hack to get the top eigenfunctions of the Hessian. Right?
And how good is this approximation?
Yeah. We have a result in AI Stats 2024 that tells you that if the size of this submatrix is something like log n power 4, then it's a good enough approximation.
So is it like Johnson and Littner's cross type thing or something?
It's more like Davis-Kahan kind of analysis
Okay.
that, yeah. Nothing, no new machinery, just
But interesting.
painful calculations to get to log n power 4. That's probably not even optimal.
Maybe slightly complicated question. Why did Nystrom approximation first come in place? Okay.
I am not sure actually. Yeah. Okay. So what does the update equation look like with this approximated preconditioned gradient descent? Earlier, I was having to update all the coefficients in the correction step, in the preconditioning step. Now I only have to update the coefficients corresponding to the submatrix that I chose to calculate the eigenvectors on. And there's an additive update that I now need to do. This is again a low rank matrix. And if you now look at what is the setup time, it is very small. S is logarithmic in n. And the memory requirement, extra memory that I need is logarithmic in n, and the flops that I need extra per sample that is processed is also logarithmic in n. So this is a problem is kind of solved. Not quite. The issue is that you require the amount of resources that you require at the time of inference in a kernel machine are dependent on how big your training data was. This kind of doesn't make sense, right? Like if I train on the entire internet scale data, it shouldn't require me those many resources to do inference on the, right? So you should, we should use something which is a truncation of sorts. So we use this thing called inducing point kernel machines. Several different communities have studied functions of this type. These are also called inducing point Gaussian processes and stuff like that. So, but this class of models has been seen several times before, and we would like to train models which are of this type rather than the classical kernel machine.
This is the P out of n.
That is the P out of n. That is, yeah. So P is much less than n. That is how you should think of P. And we'd like to, we'd have a budget for what P is, right? P is related to how many resources you have at inference time. Whereas n is how much data you have at training time. These are fundamentally two different degrees of freedom you may have access. So this paper, Falcon in 2020, showed, they have a very nice name. It's a really nicely written paper, Kernel Methods Through the Roof, handling billions of data points. They actually train very large kernel models using some very elementary decompositions in linear algebra. And they are able to scale n to very large numbers, but their P is kind of fixed. Okay, so what they have actually enabled is this thing called data augmentation, which is really necessary in practical applications of data science and machine learning. You almost always get a bump in performance when you do data augmentation. And what they've done is now enable us to do data augmentation on kernel machines as well. What unfortunately is observed in practice is that if you have more data, you also need to increase the size of your model to get the best performance. This is very similar to what is observed in the language model world. Like if you have a lot of data, you want to get the most performance out of it, you increase the size of the model in some sense. And so we would ideally like, Falcon has this one problem that it requires memory that is quadratic in P. And that is why it doesn't allow us to extract the most out of a given data set, a given large data set. And so we like an algorithm that allows us to do this in memory that is not quadratic in P. So yeah, that kind of brings me to the second part. We will now work with a setting which is the inducing points in the model specification are given to me. I am not going to choose what those inducing points are. I'm going to focus only on the part that is training, finding betas, the coefficients beta of this linear system of equations. Okay, how to choose those inducing points is actually a statistical question that needs to be dealt with separately. This is just an algorithmic question: how to choose betas, how to come up with algorithms to train these betas efficiently, both in a memory and time as the resource, right? So again, because we are wedded to this philosophy that all the algorithm design is going to happen in the function space, and we're going to track what's happening in some finite dimensional space. we're going to use the same idea now. But what Piyush was pointing to, the gradients are no longer going to be in the space that is represented in our case, right? So if you look at what is the stochastic gradient here, it is something like k dot xi times the residual, right? This may not be in the representation space here, right? So how do you actually deal with this? This is the first challenge that we need to contend, right? And what's the natural way to contend with this? We do a projection, right? So you take now there is a projection, right? So this is exactly what the algorithm looks like. So this was the this is the space, the constraint space Z that we're going to do the optimization on. It's a linear subspace. You take a stochastic gradient. Instead of taking just the stochastic gradient, you take a preconditioned stochastic gradient, which allows you to take very large step sizes also. And then you do a projection, and then you can very easily represent what this solution is, right? So you just need to figure out how to do projection in this RKHS screen. That once you know how to do projections, your life is good again, right? And then you keep continuing like this, right? So let's look at what projection actually means in the RKHS. And yeah, we're not going to do an exact projection, we're going to do an approximate projection, but yeah, let's study what the projection actually means. Okay, so here is a lemma that tells you what exactly happens when you do projection in the RKHS. So if G is some function in the RKHS, and you want to project the G onto this subspace Z, then that is given exactly by this function k dot z beta. But what is beta? Beta is the solution to this system of equations. K z z beta is equal to G of Z. You have to evaluate that function G that you want to project at all the points Z, right? And then solve this P by P linear system of equations. Okay? The proof is not very complicated. You just expand what the projection operation is. The only thing that you keep in mind is that because you're sort of wedded to this philosophy that you don't know any other geometry but the function space, the norm that you choose is the function space norm. This is not the L2 norm or anything like that. And then you can very quickly show in 2 steps that the solution is nothing but the solution to this linear system of equations.
Yeah, and I guess one can also think of this as an alternate way of proving the representative theorem, right? Because
yeah, exactly. That's exactly how you prove the representative theorem. I mean, the representative theorem is really a fancy way of saying Pythagoras theorem.
Yeah.
So, like, yeah.
Yeah. So specifically, you think of yourself as doing some kind of proximal gradient.
Projected.
Projected gradient.
Yeah.
And then
right. And now, how do you solve this linear system of equations? This is just the kernel machine that we saw earlier, right? So EigenPro version 2 was designed to solve kernel machines where the data are Zi, Gzi, right? Okay, and you can solve this projection subproblem using this EigenPro version 2. We did that. It looks like this. It has some, again, you do a lot of bookkeeping to keep track of all of these iterates in the function space and how to track them. But you just have to do that once. And this is what it looks like. The setup time is small. The memory requirement is now better. It is independent of n, which is your training data. But the problem is that the number of flops per sample is something like p square over b. B is the size of your batch. Okay? You can increase b, but there is only a limit to which you can increase the batch size because again you see a saturation that is happening again. So you really need a fundamentally different approach to tackle the problem of getting rid of this p square term for very large models. Okay. Yeah, and what we see in practice is as soon as you keep increasing the model size, you keep getting better and better performance. At some point it saturates and then you increase the model size again and you get better performance from that bigger model. Somehow over the last 5-6 years, we've gotten comfortable with this as the way of life. 10 years ago, maybe this would have been almost a taboo intervention to make. Okay, how to choose P? How many inducing points you actually need? That itself is an open statistical question. Somebody should look at that question as well. So yeah, we are now at a point where EigenPro version 3 can train models which are very large. But for smaller models, Falcon is still a better algorithm. Just for some numbers, when you had 128 as the number of as the size of the model, Falcon was taking only 21 minutes. EigenPro version 3 was taking 5 hours, 41 minutes. It was extremely slow, but yeah, it was a new design idea and it actually led to something better in the next part. So what do we actually do? Instead of projecting after every step, we amortize the projection cost. The p square cost was actually the cost of projection, and instead of projecting after every batch, you project after several batches. What you need to do is you need to know how to actually represent each of these intermediate functions. And once you're here, you just have to evaluate that function at all the z's, and then you can solve an approximate projection and get here. Right? Okay, so again, in the interest of time, I won't show you the derivation. It looks, we've done the effort of deriving what that algorithm looks like. What we now have is this new algorithm, EigenPro version 4, which represents all those intermediate things smartly. The number of flops per sample is now, again, 3 times p instead of p. The memory is 2 times p instead of p, but it's all linear in p. And so this is scalable in terms of the size of the model. Yeah.
What are those metrics?
No time right now, but yeah, they are essentially eigenvectors, the small eigenvectors of the submatrix of the kernel matrix. Yeah. Okay. So yeah, here is the summary of all the papers that we've written over the past few years. Yeah, so this is the first EigenPro version 3, which allowed us to even solve the problem by getting rid of this initialization cost and the memory requirement. EigenPro version 4 solved the problem of time. We still required number of steps, which was kappa q, and we know that there is a lower bound of square root kappa q that you can achieve that when you add momentum to that as well. And the algorithm becomes a little more elaborate. You have to write more steps, but the resources that you actually require to implement momentum is not significantly large. The number of steps is still square root kappa. So there is some benefit in doing momentum. We're writing a version of this algorithm where that extends this to, the story was so far was only about square loss functions, right? You can extend this to arbitrary convex loss functions as well. And well, we don't quite exactly know what this quantity should be, but yeah, this maybe in a month or so, we'll have a clear picture of what this is. In doing so, we also proved a theorem which says that the size of the submatrix that you need to choose to approximate your preconditioner is logarithmic. Okay, some numbers that I shared earlier. So EigenPro 3 was taking us something like 20 days to solve this problem. Now it takes us 1 hour to solve that same problem. And yeah, so these are like very massive speed ups that now enable us to train these very large kernel machines, which was not possible earlier. Yeah, I'll end my talk with some open questions. Performance is the same because we are training the same problem. Yeah.
If I may ask, did you compare with them?
We did compare with neural nets. Our performance is still not as good as neural nets because the kernel function that we've chosen here is fixed.
Yeah.
There is an entire separate machinery that needs to be run to choose a better kernel function. That's a separate talk. But yeah, this solves one sub problem in getting some comparable performance to neural networks. Yeah, so some open questions. Can we repeat the new show for other types of spaces? Something like reproducing kernel Banach spaces, where duals are not nicely defined. Can we do some kind of mirror descent type of approaches? Can we actually implement those and track them in the same philosophy? Does this imply anything for neural networks? Can we get better preconditioned gradient algorithms for neural networks? And this was all in a setting where the cost of computing each kernel function, kxz, was sort of cheap. And there were some unknown constants in my evaluations which assumed that the kernel evaluations are cheap, but there are some newer kernel functions that we've now hit, which require expensive calculations just to get the kernel function itself. Can we come up with other types of algorithms that are aware of the cost of computing the kernel and optimized with that cost in mind? Thanks.
You already had many questions, but are there any more questions?
I have a question. So these experiments that you did, they were not for this Sobolev space on Mars, right? They were some
No, yeah, they were on the Laplace kernel,
close to Laplace.
on RD.
So is there any merit in doing that, in doing it on things like Sobolev spaces?
Yeah, like the Sobolev spaces are nice when you have small dimension. I don't know much about Sobolev spaces beyond that they are RKHS. They're kernels for RKHSs. But yeah, like the Laplace kernel is what seems to work best. The reason to choose the Laplace kernel is that the NTK for fully connected networks and the Laplace kernel span the same RKHS, span the same space of functions with a different inner product.
Yeah, I think maybe one reason why this I would have asked similar questions, Hari, is that just how much kernel independence can you get here? Because like Sobolev space doesn't have to define a kernel first. You first come up with some other natural property of a function that it should be C2 and stuff, and then out pops a kernel.
Right. So typically, the way a practitioner would approach the problem is not by first defining the RKHS, I guess. They would start by defining a similarity metric. But yeah, I mean, I don't know whether to start at the RKHS or whether to start at the kernel. Yeah. Is there a reason to actually consider Sobolev spaces over the Laplace kernel, maybe?
When Heidi mentioned these Sobolev spaces, don't you need the power of P also to be large for good extension?
You do, yeah. Yeah.
It won't be a inverse.
Yeah, you have to have like extremely smooth functions. You can't deal with like small order. Yeah. So that's another reason to,
Let's hand this.
There is one that I want to do. So, PFR students, we are organizing this